All right, let's jump right into this explainer. Welcome. Today we are exploring a genuinely revolutionary mathematical framework. We're talking about something that finally bridges two incredibly complex worlds of mathematics that historically have barely even spoken to each other. We are looking at a brand new paper called Prometheus, a coupled Wasserstein-Riemannian variational model. This was put together by an independent researcher, Mohammed Ben Ammar Shradi, and you can actually reach him directly at magnioproject@gmail.com. If you've ever geeked out over how algorithms understand complex data geometries, you are absolutely going to love this. To really wrap our heads around this, I want you to imagine an explorer trekking across a massive, rugged mountain landscape. Now, normally we think of the landscape as fixed, right? The mountains, well, they don't really care that you're walking on them. But what if our explorer was so heavy, so massive, that their very footsteps permanently warped and bent the ground they walked on? And then, in turn, that newly warped landscape immediately dictated where the explorer could take their very next step. It begs a fascinating question. What if data could actually shape the space it lives in?
Now, you might be wondering why this is such a big deal. Well, it exposes a pretty massive gap in our classical models. You see, in classical optimal transport theory, we're really good at figuring out the most efficient way to move a distribution of mass. That's our explorer. But the metric space itself is totally rigid. It's stuck. Conversely, if you look at geometric analysis, like Ricci-Flow, the landscape evolves and smooths itself out beautifully, but the distribution of mass is completely ignored. It's frozen. Prometheus comes along and asks, why on earth can't we do both at the exact same time?
So, here is our roadmap for today. First, the geometry data disconnect. Second, enter Prometheus. Third, the mathematical engine. Fourth, the Dieterk gauge fix. Fifth, a quick JKO splitting scheme tutorial. And finally, validating the coupled dynamics.
Okay, starting with section 1, the geometry data disconnect.
So the absolute crucial point here is that in fields like metric learning, information geometry, or even modern generative AI, the geometry and the data distribution are totally intrinsically linked. If we want a machine learning algorithm to truly understand data, the underlying metric literally has to adapt to reflect how that data is concentrated. If we just force our data to live in a predefined rigid space, we're basically ignoring an entirely new dimension of optimization.
Which brings us nicely to section 2, enter Prometheus.
Enter Prometheus. This is a coupled Wasserstein-Riemannian variational model, again introduced by Mohammed Ben Ammar Shradi. In this completely unified framework, a probability measure, which we are going to call mu, and a Riemannian metric, which we'll call g, actually evolve simultaneously under one single energy functional.
And this brings us right back to that explorer analogy, beautifully illustrating the whole concept. The model basically creates this continuous real-time feedback loop. The probability measure is evolving in the two-Wasserstein space, while the metric is simultaneously adopting in an infinite-dimensional manifold of metrics. It's a completely coupled evolution.
Let's dive a bit deeper in section 3, the mathematical engine.
So how does this actually work under the hood? Well, the total energy functional of Prometheus relies on three very specific components working together like a well-oiled machine. First up, the non-local kernel-weighted entropy. This is really the heart of the interaction. It couples the measure and the geometry using a smoothing kernel, which means the density's variation is tied directly to the metric's volume element. Second is the Einstein-Hilbert functional. You can think of this as a curvature regularizer. It smooths out the scalar curvature of the metric over time. And finally, the subobal penalty. This acts as a sort of coercive anchor. It basically ensures our evolving metric doesn't just fly off into mathematical chaos, keeping it positive, definite, and reasonably close to a baseline reference metric.
Moving right along to section 4, the Dieterk gauge fix. Now, of course, doing this creates a pretty major mathematical hurdle. It's a problem known as diffeomorphism degeneracy. Because that Einstein-Hilbert regularizer we just talked about is diffeomorphism invariant, the math essentially creates a glitch. The coordinate system simply loses its reference points, meaning the metric evolution equation is no longer strictly parabolic. To de-jargon that a bit, without a fix, standard parabolic existence theory fails entirely, and the whole mathematical engine just grinds to a halt.
So, how do we fix it? The author brilliantly applies the Dieterk trick. By adding a highly specific Lie derivative term into the metric equation, the Dieterk gauge essentially locks down the coordinate system. It's exactly like a mathematical anchor that stops our coordinate map from spinning out of control. It restores that strict parabolicity to the system so the geometric flow can actually be computed safely.
It's an incredibly elegant fix that's been borrowed from Ricci flow literature and adapted perfectly for this coupled system. Next up, Section 5, JKO Splitting Scheme Tutorial.
Okay, let's actually walk through how you compute this over time. The author proposes using a Leitrotter JKO splitting scheme to simulate this in discrete time steps, and it alternates back and forth beautifully between moving the mass and warping the space. Step 1, you freeze the metric and update the measure using a Wasserstein proximal step. Essentially, you're moving the data. Step 2, you freeze the measure and update the metric using a Dieterk-modified explicit gradient descent. Now you're warping the room. And finally, step 3 is a quick projection step to ensure that newly updated metric actually remains a valid, positive, definite tensor.
And hey, for those of you actually looking to implement this model yourselves, the paper gives a great guide for using standard computational tools on a 2D flat torus. You just discretize via an n by n Cartesian grid. Your probability measure becomes non-negative cell masses, your metric is represented cell-wise as a full symmetric 2x2 tensor field, and all those wildly complex differential operators? They're handled cleanly using centered periodic finite differences. It is a super robust way to put the model to the test.
Finally, let's hit Section 6, Validating the Coupled Dynamics.
Take a look at these results from the baseline experiment running over time, moving from left to right. Notice what's happening in the top row. The probability density doesn't just diffuse out into a messy blur. It sharply concentrates into these highly localized profiles. And meanwhile, in the rows below, the scalar curvature and the off-diagonal metric components rapidly decay and become numerically tiny. The data is visibly concentrating, while the geometry is flattening and adapting at the exact same time. It's awesome.
And this right here is what absolutely proves the stability of the model. These energy charts show us exactly what we want to see. Look at the total energy of the system. It beautifully and globally decreases over time. Furthermore, that Dutra correction term remains incredibly small throughout the process. That proves our coordinate gauge fix is working perfectly as a perturbative anchor, doing its job without overwhelming the actual dynamics of the system. So, Prometheus totally proves that we no longer have to choose between moving our data or warping our space. We can do both. I want to leave you with this provocative thought. If our algorithms can rigorously co-adapt data and geometry simultaneously, what completely new frontiers in unsupervised metric learning and generative AI are we going to cross next? Thank you so much for exploring this fascinating framework with me. Definitely make sure to check out the original paper by Mohammed bin Amar Chayedi if you want to dive even deeper into the math. Catch you next time.